All right, we are getting close to one of my favorite topics. One of the reasons, of course, I'm teaching this class is because I have so many favorite topics in this class. Okay, so we were talking about expectation. We had a conjecture, right? Toss n independent pair coins, and the expected number of heads we thought was n over 2, or more generally, we thought it was n times p. And there are a lot of ways to prove this. So I'm going to show you the simplest way first, then I'm going to show you a much more complicated way. And why am I going to show you the much more complicated way? Oh, they're both rigorous, but a good guess. Why am I going to show you the more complicated way?
Because it illustrates more of the mechanics behind why it works.
Not so much the mechanics about why this works, but it gives you another technique. And for other problems, this technique will be very important. And so it's worthwhile seeing something multiple ways. So here's the simple proof. Let's let x be x1 plus xn, where xi equals 1 if ith toss is a head, and 0 if ith toss is a tail. And if you want, we can do this with probability p, and this would be probability what? 1 minus p. And so clearly, x is just x1 plus xn. Right? The total number of heads is how many heads I get in the first toss plus how many heads on the second toss plus dot 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 plus how many heads on the nth toss. The mission review dinner tonight will probably be starting around 6:15 as Cam has soccer. His homework problem is to roll die and record the results. So there will be some die games going on at mission tonight. And I will bring sheets in case people come and want to rumble. We agreed that x is the sum of these. Okay? But the expected value of x is the expected value of the sum, I goes from 1 to n, of xi. And what does this equal? So the expected value of a sum is? So the sum so I will write over here, must prove. Right, we haven't proved that yet. But now we can begin to see why we want to understand this. How many of you have taken a chemistry class? Just 1, 2, 3? Okay. Oh, wow. Interesting. Takes a while to have that propagate. Chemistry.
Well,
I think I took chemistry. Yes, yes, I did take chemistry.
As a non-majors chemistry.
As a non-majors chemistry class. That's fine. So in chemistry class, you break things down into... What do you break things down to in the chemistry class? Atoms, right? And if you want to break things down in the atoms even further, you break them down into protons and neutrons, and you want to break those down further?
Then we're getting to physics
Quarks.
territory.
Now you're getting to physics, all right. Then you get in strings, Higgs field, Nobel Prizes in physics. You break complicated things into simpler things, and then you understand how they combine. That's exactly what we're doing here. We're breaking a very complicated process. This is really complicated. We're tossing, n coins simultaneously. It's very complicated. Into something much simpler. We're tossing one coin. Okay? I understand tossing one coin. And by understanding the tossing of one coin, I understand the tossing of many coins. I no longer have any combinatorics. I no longer have any n choose k's that I have to evaluate. We no longer have those sums. Well, what's the expected value of x1? It's the same as the expected value of x2. It's the same as the expected value of x3. They all have the same expected value. So the expected value of xi, well, I can get a 1, which happens with probability p, and I can get a 0, which happens with probability 1 minus p. So I just get p. So we can conclude the expected value of x, the number of heads we expect to get, is just the sum I goes from 1 to n of p, and that's just np. And so that's a proof. But what does this proof use? It uses linearity of expectation. So proof uses linearity of expectation. So we need to prove that. And so, since some of you may not have taken a proof-intensive course, I want to give you a small little humorous digression on the need for proofs. Okay? I'm going to test your algebra. I know it's early in the morning. 16 over 64. 1/4. All right. 19 over 95. 1/5. 49 over 98. Half. 12 over 24. Sorry? 1/4, right? I did stay up late watching the Red Sox, and I stayed up late watching the Red Sox celebrations and recording it, so I may be a little bit tired, but I get 1/4. Alright, let's check. 16 over 64, cancel the 6's, get 1/4. 19 over 95, cancel the 9's, get 1/5. 49 over 98, cancel the 9's, get, yes. So this is 1/4. That's how I divide. Right?
Yeah. Exactly.
Yes.
Yep.
Yes. This leads to a grade that is bounded by D. Just okay. Just because you check something for a couple of cases does not mean it works. Okay. We need to be able to justify switching. Just because it works in this problem does not mean it's always justified. I'll give you an example later with variances, where it looks like the variance of a sum is the sum of the variances, but that's not always true. It's only true in certain cases. So you've got to be very careful. Is the square root of a plus b typically equal to the square root of a plus the square root of b? No. Typically no. Easiest thing to try is to try Pythagorean numbers. The square root of 3 squared plus 4 squared, that's 5, and it does not equal the square root of 3 squared plus the square root of 4 squared. So just because something passes a test or two does not mean it's correct. So you want to be very careful about making mistakes like this. Okay, so what I want to do now is I want to prove linearity of expectation. And that will give us this theorem, and it will give us many other things. There's going to be a lot of fun applications of linearity of expectations. How many of you have ever had, cereal or, some, product where they have different toys inside? This will allow us to completely understand this problem. When you have two little kids who want the same toy, trust me, this is a very useful thing to know how many cereal boxes you will need. Okay? Linearity of expectation. Assume each xi has finite mean, then the expected value of the sum, I goes from 1 to n of xi, is the sum, I goes from 1 to n of the expected value of xi. So if you could put down, your wish list of theorems, this is what you would love. And it's going to allow us to explore a lot of problems in terms of simpler building blocks. So there's lots of different ways to prove this. I'm going to assume my random variables are continuous just for the proof. What else would I have to look at? So that's a good question. Is that in my list of assumptions? No. That's one of the reasons why this theorem is so great. I do not need to assume independence. Okay? But I'm going to assume for the proof that the x's are all drawn from continuous random variables. What else would I have to look at? And what else?
Mixed.
Mixed. Right? I'm only going to do the case of continuous. The proof is the same in all the... So proof. Assume continuous with joint, bless you, density function f of x1 to xn. So we're finally going to get to use our joint density functions. Okay? The expected value of x is just the integral, I'll go from minus infinity to infinity. Then the expected value of x is just x1 plus xn f x1 xn x1 xn dx1 dxn, right? This, I look at all possible tuples. This is the probability I got that tuple. And if I got that tuple, what is its value? Its value is the sum. Okay? So now what's the next step? I have this integral of a sum.
Break it up.
Break it up how?
Into each individual x1 plus x.
So I want to switch orders. Okay? One of the most powerful techniques we have is switching orders. Okay? And so now if I switch orders, this becomes a sum. I goes from 1 to n, the integrals. Now it's just xi, f of x1, xn, x1, xn, dx1, dxn. So I have to be able to justify switching the order of integration. The reason I can justify this is if I put absolute values, everything will be okay and finite. So the justification, and we'll see later, is if use absolute values, it's finite. So I'll go through the proof now, and then you can see that if we put in absolute values, we would have gotten a finite number. We can then appeal to Fubini's theorem. All right. You have n integrations to do. We're going to play Sesame Street now. Okay? One of the skits they have in Sesame Street is one of these things is not like the other. One of these things just doesn't belong. When you look at these n integrals, right? I'll try to remember to put in a YouTube clip. Which integral, which variable looks different than all the others? The xi. So let's switch the order of integration and let's integrate over xi last and integrate over everything else first. Well, when I integrate over everything else first, I'm basically saying fix xi and integrate out everything else. We have a word for what we get. What do we get when we do that? It's the marginal. So fix xi, switch integration to have the integral over xi last. The other n minus 1 integrals give the marginal of xi. That's great. The marginal of xi, that's just the density of xi. Is this in your way? No? Okay, good. Okay, so now, when we do those integrals, things are going to be very nice. We'll be left with a one-dimensional integral. And so what we get is the expected value of x is now going to be the sum, I goes from 1 to n, the integral xi goes from minus infinity to infinity, xi, and now we have the marginal density of xi. Everything else integrated away. If I didn't have the xi here, what would this integral be?
Wait, everything else integrates to 1?
So everything else integrates to the marginal density of f of xi. So it integrates to the marginal density of xi. Just integrates away. Because I'm saying I don't care about the other values, I only care about the value of xi. So when we integrate the joint density function over everything but one variable, we're left with the marginal. If you go back to our coin tosses, this was just going along the rows or going down the columns. So if I didn't have the xi here, what would that integral equal? 1. I have the xi here, what does it equal? So I'm integrating xi times the density. This is just defined to be the expected value, which is exactly what we want. So we get the sum, I goes from 1 to n, of the expected value xi. And that's what we were trying to prove. The only thing we have to be careful about is, were we justified? So what I'm going to do is I'm going to just show you the justification. So if I put absolute values here, if I bring the absolute values inside, I only make things larger. And then over here, the absolute value of a sum is less than equal to the sum of the absolute values. So then over here, and this is the expected value of the absolute value of xi. And whenever we talk about the expected value existing or the mean existing, we always assume that this integral is finite. Remember we had the Cauchy distribution? And if I wanted to, depending on how I send my bounds to infinity, I could get the integral to converge to whatever I wanted. This is a really bad improper Riemann integral. Okay? Over here, if I'm saying the expected value exists, I'm assuming the integral of the absolute value is finite. And that's the condition I need to appeal to Fubini's theorem. Okay, any questions on this proof? We now know the expected value of a sum is the sum of the expected values. This is great. Yes?
What is Fubini's theorem?
So Fubini's theorem, if I have the integral, say from a to b, c to d, f of xy dy dx, this is the same as the integral from c to d, integral from a to b, f of xy dx dy. So the question is, when am I allowed to switch the orders of integration? Did I do the example in class about sums when you can't switch the order of sums? Okay. So if there are infinities going on, then bad things can happen. And so this is, you're okay if the integral from a to b, the integral from c to d, of the absolute value of f of xy dy dx is finite. So as long as that's finite, you can then switch the orders of integration. There's a couple of things you really need to learn to put in your tool bag if you're going to be a professional mathematician. One is, when can I switch orders of integration? Another is, when can I switch orders of, say, differentiation and integration or differentiation and summation? These are extremely powerful techniques. And so we're going to see an example of switching derivatives and integrals very soon. So if you want, I can actually go straight to that, to the method of differentiating identities, or we can do variances first. I have absolutely no preference. Whoever speaks up first wins.
First one.
First one. Do you even know what the first one was?
Something about derivatives.
Okay. I've got to be careful because this is being recorded. My wife might actually, listen to this. But sometimes when I'm asked for my input on couch fabrics or whatnot. Oh yes, the second one. And the number may be chosen before the question is asked, and the choices are presented. But you always have to have a justification for your choice. Okay. Differentiating identities. This is an absolutely amazing technique. Okay? It is incredible how many things this could do. If I were to do like a TV show, one of these networks about things to buy, this is what I would try to sell people. Okay? And I would be able to make a very compelling case that of all the techniques you want to learn, this is the one. It will solve so many difficult problems very simply. So consider the following. The sum, n goes from 0 to infinity, of n over 2 to the n. I want to know what that sum is. I thought about this a few days ago, and it is possible to evaluate this sum without knowing calculus by using the basketball problem. And so if there's interest, I will show you a backdoor of how to evaluate this. Now the first question you should have when you see the sum is... Yes?
Does it converge?
Nope.
Is it finite?
Nope. Who cares? First question should be, who cares about a sum like this? Alright, then after that, then you can...
What is the real world application of this problem?
Well, good. Why are we doing this problem? Who cares about this? Now, given that I've convinced you, for the sake of argument... I took econ classes. I'm allowed to assume things, yes. So given that we care about this problem, now what question would we ask? Abraham?
Does it converge?
Does it converge?
Is it fine?
Is it fine? Okay, now we would ask a question. So I will give you an example of why you might care about this. Let's consider probability P of success. Do I want to put this right? No. 1 minus P of success. This is a little bit annoying, but 1 minus P of success, P of failure. And actually, let's use the letter Q and 1 minus Q. Because it's just wrong to use P as the probability of failure. Okay? How many of you have read Waiting for Godot? So you have the scene where they keep flipping coins and keep getting heads, 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 over 90 heads in a row. So what I want to do is I want to wait until my very first success. I'm going to keep flipping a coin, and as soon as I get a head, I will jump for joy, and the game will be over. And I want to know how long do I have to wait before I get a head. So we're basically trying to model how long until something happens. There are a lot of real-world applications where you have something like that. You know, at each moment in time, you have a certain probability that success happens. How long do you have to wait before it's success? Think of it as waiting in line for something. So what's the probability the first success is on the nth toss? So what's the probability that my first success is on the nth toss? What would that be?
That'd be,
In fact, let's do it on the n plus first toss.
are we...
Can we have a success on the 0th toss?
No.
No. So let's do the first success is on the n plus first toss.
Is this coin fair?
Nope. Probability 1 minus Q of success, probability Q of failure. And we'll assume the tosses are independent. So what's the probability your first success will occur on the n plus first toss? Yes?
Well, it would be Q to the n times 1 minus Q.
Okay. So basically, failure, failure, lots of failures, and then a success. Okay? So this is the probability that my first success is on the n plus first toss. And you can see why it's actually better to write it as n plus 1 rather than n. Because you're not going to get a success on the 0th toss. I don't care how good you are. I don't care what the value of Q is. You have to toss the coin at least once. Alright? If I want to calculate the expected value of x, that's the sum. N goes from 0 to infinity. N. And now the probability of a success on the nth toss is just Q to the n, 1 minus Q. When you see this, what do you want to do? So I've got this sum. Any part of the sum easy to understand? Yeah, pull that outside. And you get 1 minus Q times the sum. N goes from 0 to infinity of n, Q to the n. That looks very much like what we started with. So we can actually cast this as a specific example here. And it would just be the case where Q equals 1/2. So one question is, why should I recast this more generally? Why should I change 1/2 to a parameter Q? So again, you've all taken at least 3 semesters of calculus, right?
If it's 1/2, don't you have an extra? What? The 1 minus Q?
Yes, so I would have an extra factor of 1/2, correct. And so I would then have to adjust the answer by a factor of 1/2, which is not a huge deal. But you do have to be careful that you do have this extra 1 minus Q floating around. And when I was actually looking at the non-calculus approach, it took me a while because I forgot about that for a moment. But we've spent a lot of time proving calculus results. I want to have them at my disposal. I want to be able to use them. If I replace this 1/2 with a parameter, all of a sudden I can vary things. And if I can vary things, what can I do? Differentiate, right? This is the section on differentiating identities. So probably differentiation is going to be important. So let's consider the following. the sum, n goes from 0 to infinity of x to the n. What does the sum equal? So what does the sum equal? This is the geometric series.
1 over 1 plus x.
1 over,
To the,
this should be memorized. You know, you should have mother's name, father's name, siblings, best friends, geometric series formula. Maybe not in that order.
or minus x.
So it's 1 over 1 minus x, 1 minus x inverse. Okay? That looks a lot like this. What do you think x is going to be? 1/2. Now, what's the difference between this and this? How could I get from that series to this series? So let's rewrite this as n times 1/2 to the n. Any suggestions on how I could get something like that from this? What do you want to do to this?
Take the derivative.
Take the derivative. Now if I take the derivative, what happens to x to the n? It becomes nx to the n minus 1. So what I'm going to do is I'm going to apply the operator x d by dx. And the reason I'm going to multiply by this extra x is I'm going to keep the power of x as n, which is what I want. Okay? Now, what do I have to worry about? I have x d by dx of the sum. What do you think I want to do with my operator?
Pull it inside.
I want to pull it inside. So this has to be justified. So the sum n goes from 0 to infinity of x d by dx of x to the n, and then that would be the same as x d by dx acting on 1 minus x inverse. So must justify. So in the book I have a couple of pages that justify interchanging the sum and the derivative. It turns out in the case of the geometric series, this is the simplest case to justify. What you do is you truncate the geometric series at a large number n, and then you look at the tail. And the tail is going to be a geometric series as well. So we'll just briefly sketch the justification. The sum, n goes from 0 to infinity of x to the n, is the sum, n goes from 0 to n of x to the n, plus the sum, n goes from n plus 1 to infinity of x to the n. And this is the sum, n goes from 0 to n of x to the n, and this is going to be x to the n plus 1 over 1 minus x. You only have finitely many sums. We can interchange a derivative with finitely many sums. And then you take the limit. So, finite number of sums can interchange, take limit as n tends to infinity. Okay. So it can be justified that the derivative of the sum is the sum of the derivatives. Alright, well now what do we get? We get the sum, n goes from 0 to infinity, of n x to the n, and now I take the derivative of 1 minus x inverse. The negative 1 comes down, I get 1 minus x to the negative 2. I take the derivative of the inside and I get another negative 1, because the derivative of 1 minus x is negative 1. So when the dust settles, this equals x times 1 minus x to the negative 2, or x over 1 minus x squared. And we've just found a new formula. So what value should we take for x? If x equals, what should we choose? 1/2. If x equals 1/2, we now get the sum, n goes from 0 to infinity, of n 1/2 to the n, 1/2 over 1 minus 1/2, which is 1/2 squared. We just get 2. So you can use that to calculate the expected value of this process. Okay? This is not a one-time trick. This works for a huge number of problems. I could spend, I think, 2 or 3 weeks just going through all the different places where differentiating identities works. Let's do at least one more example. What was the first problem we studied today? What were we looking at? Tossing an independent coin. Let's do that one. So the expected, so we'll do coin tosses. The expected value of x is the sum. K goes from 0 to n. What's the probability we have exactly k heads? So it's k times the probability x equals k. That's our definition for the expected value. So this is the sum, k goes from 0 to n, of k. And now the probability that I have exactly k heads in n tosses, I choose k of the n to be heads. We'll do the general case, p to the k, 1 minus p to the n minus k. Okay? We're going to figure out what this is by differentiating identities. And there's going to be an advantage between this and the infinite sum we had over here. This is finite. Do I have any danger or any difficulty justifying differentiating a finite sum? No. So life is going to be a lot better here. So I've commented earlier that it is very difficult in general to prove inequality. And once you get an equality, you want to mine it as much as possible. What other equalities does it imply? Okay? So the geometric series formula, we actually got a new equality from it. What could we do next? Differentiate again. And we would get something for the sum of n squared x to the n. So we can actually now figure out the sum of n to the l x to n to the l x to the n for any l. We can just keep applying it. The whole point was we needed to have an equality to start with. I need an equality to start with to attack this problem. Can anybody think of any equalities we have that are close to this? I need an equality that's close to this. Any thoughts? What does this look like? I'm sorry? The binomial. So let's start with the binomial. Now how would you write the binomial? So how should I write the binomial theorem? I'm sorry?
It's just the same thing except for not the k.
Okay, and then what would that equal? So if I don't have the k, what does this equal? So I'm summing n choose k, p to the k, 1 minus p to the n minus k. What does that equal? You should all be able to answer this. So if I'm removing the k, I'm summing the probability x equals k over all possible values of k. It's got to be just 1, right? This would be, but the binomial theorem would tell me I would just get p plus 1 minus p. So I would get the function 1. Do I want to apply derivatives to the function 1? Probably not, because if I apply the derivative, it's going to completely vanish. So what I'm going to do is I'm going to set it a little bit more general, and then I'll specialize. This is very similar to what we did. I want to understand the sum of n times 1/2 to the n. I consider something a little bit more general. I'm going to start off with something a little bit more general. P plus q to the n is the sum, k goes from 0 to n, of n choose k, p to the k, q to the n minus k. Now, in the back of your mind, what are you thinking of every time you look at q? Right, don't do this in an English class, but in a math class, every time you see q, you should be thinking 1 minus p. Why am I not writing 1 minus p right now? If I write 1 minus p right now, I would just get 1 on the other side. I want to give myself a little extra freedom. I want to differentiate. What do you think I should differentiate with respect to? P or Q?
P.
P. Because if I differentiate with respect to P, I'm going to bring down a K. That's exactly what I want. If I had a 1 minus P over here, if I differentiate with respect to P, I'm going to get a product rule. I don't want that. Right? Is it possible to solve the problem using 1 minus P instead of Q? Strongly encourage you to try to do that. But you can see the algebra is a lot worse. This is why I really want to hop on this. This is a great way to attack the problem. Do I want to differentiate with respect to P, or do I want to do something a little bit close to that, but not quite that? What should I apply? So if I differentiate with respect to P, I'll get K P to the K minus 1. Is that what I want? What do I want?
Also multiply by.
Yeah, so I think it's much better to apply the operator P d by dP. I've got to be a little bit careful here. Should I be writing full derivatives with respect to P or partial derivatives with respect to P? I think I should probably write partial derivatives if I'm going to consider Q as a variable. And so I would apply maybe P partial with respect to P. Alright, so if we apply the derivative with respect to P on the left, we get n, P plus Q to the n minus 1, and the derivative of P plus Q with respect to P is just 1. On the right-hand side, we get the sum, K goes from 0 to n. Now I apply partial with respect to P and multiply by P. I can pass that through the sum, and I'll just get K, and choose K, P to the K, Q to the n minus K. Question?
We forgot to multiply by P on the left.
Oh, yeah.
Oh, yes, thank you. I forgot to multiply by P on the left. Yes, thank you. We would have had a catastrophe where all of a sudden mathematics would not be consistent. Okay, good catch. This equality holds for all choices of P and Q. So I wanted Q to be a variable so I could apply the operator. But now that I've applied this, I have this equality. I can choose any value of Q I want. What's a good value of Q to take? 1 minus P. So now, if Q equals 1 minus P, I get n times P. What's P plus Q to the n minus 1? If Q is equal to 1 minus P, it's just 1. And I get the sum, K goes from 0 to n, K, n choose K, P to the K, 1 minus P to the n minus K. Okay? There's the expected value. We didn't have to use linearity of expectation. We found a way to evaluate the sum of K choose times n choose K. There's a whole slew of problems that this can attack. You can calculate means of a lot of random variables. You can do it for exponentials, for normals. So many different things. Any questions about this technique? So again, if you tried to calculate the sum directly, I had some fun when we tried to do it with n equals 1, 2, and 3, and just writing out all the different terms, detecting a pattern. This allows us to handle them all simultaneously. Okay, what I want to do now is I want to return and do some variances, just because it's nice to see when things don't work out as nice. Variances. So, x1, xn, random variables, a1, an are real numbers. Assume all means and variances are finite. Technically, I don't think I have to assume the means are finite, because if the variance is finite, then implies the mean has to be finite. I don't really, yes?
What's the word after x, Abby?
all real numbers. Oh, random variables. Oh, RVS is random variables. RVS is random variables. And I'm going to, so if the variance is finite, the mean has to be finite. Okay? Then, I could look at the variance of A1, X1 plus AN, XN. If life were good, what would this equal?
1.
So, no matter what you combine, the variance is always 1.
Yeah, I mean, it's if life was really good.
I don't know if that would be really good, though. That would be a little bit too constraining. Variance of 0 is even worse. They'll be the subject of thermostatics. If you could choose the sum of the variances, what do I do with the A's?
Distribute out.
Take them out. So we'll call this hope 1. Okay, so A1 variance of X1 plus AN variance of XN. Most of you are not going to use most of the material you learn in my class. Hello, posterity. Okay? I have this desire to be brutally honest with you. Okay? Most of you will not use most of the material. Now, this begs the question, why are you in this class? I'm glad nobody's heading for the door. Okay? Some of you will use the material. What really matters is thought processes, is looking at how to attack problems. This is why I don't want to just jump in and say what the theme is. I want to talk a little bit about what you would expect. How many like this? Variance of a sum is the sum of the variances, and I pull the A's out. This has a major issue with it. Yes?
So that's just the variances for squares?
I'm sorry? So we'll get to that. So it turns out that the variances, the A's have to come in as squares. What could go wrong if I just pull out the A's? So let's do a special case. The variance of -1 times x would be -1 times the variance of x. What's wrong with this? Variances have to be non-negative, right? The variability is negative. When you take the square root to get the standard deviation, you get an imaginary number. The average height of the American male is 5'7.5" plus or minus √5i inches. Okay? You can't have something like this. What's the easiest correction we could do? Absolute values. So if we put in absolute values, so this would now become hope 2. A1 variance of x1 plus absolute value of an variance of xn. Okay. Now at least it will be non-negative. Okay? I claim, however, that this can't be right either. So can somebody give me an example where this should be wrong? Yes.
If you have them like alternating, -1x1 plus 1x2.
Okay.
-1, and if all of the xi's were equally weighted, then you just have a variance of 0.
Okay, so that's actually a deeper issue. So what you're saying is, well, what if x1, x2, x3, x4, what if they're all the same value, and I have an alternating sequence of a's? So in fact, all of this stuff is going to crucially assume independence of the x's. And so you're absolutely right that if there are dependencies, there's no way that this can hold. So let's assume the x's are independent and try to find another issue. So, again, special case. Do I want to look at the variance of -1 of x again? No, so there was somebody who was saying that maybe it should be squares. So if I try to look at -1, the absolute value of -1 and -1 squared are the same. So that would not be a good thing to look at. So I need a better number to look at. What's a better number to look at? 2. Right? Almost any number would work. The only numbers that won't work would be 0, 1, and -1. As long as you stay away from that, you will give me a good answer. The variance of 2x, do you think that this equals 2 times the variance of x? Or equivalently, the standard deviation of 2x would now be square root of 2 times the standard deviation of x. So imagine I measure everybody's height in phalanges, okay? And the average height is 100 phalanges, and the standard deviation is plus or minus 10, okay? So it's 100 plus or minus 10 phalanges, okay? I then decide to measure people in a new scale. Aliax. Okay? And in aliax, one phalange equals 2 aliax. Okay? So we now have 200 plus or minus 20 aliax. It makes sense that if I've doubled the units, I've doubled the standard deviation. But what this is telling me is the standard deviation would increase not by a factor of 2, but by a factor of square root of 2. So this simple example tells me I don't expect a formula like this to hold. It has the wrong units. Okay? So maybe we guess instead of absolute value of AI, use AI squared if independent. Okay, and so that's going to be a huge assumption that the different random variables are independent. If they were dependent, as we said, we could just look at x minus x. What's the variance of x minus x? 0. And the variance of x plus x would be probably different. And so this would not be able to detect any issues like that. Okay, so I'm going to hold off on the proof of this until next time. What I'm going to do is I've got 1 minute left. I figured I would show you the non-calculus proof of the marble problem from one of the old homeworks. You have 50 reds, 50 blues. You want to maximize. So here's the non-calculus proof. 50 red, 50 blue. You put some number of marbles in each jar. What's the best probability you could have in one jar for reds?
1.
1. You can't do better than 100%. If one of them is above 50% for reds, what do you know about the other one? It has to be below what? Below 50%. So the theoretical best you can do is half the time you get 100 and half the time you get 50% for 3/4 or 75%. This is the theoretical best. I can't do better than 75%. Okay? So let's see what's the best I could do in practice. The best I could do for this one is 100%. Now for the second one, I need a number less than 50%. What's the best number less than 50% I can get? 49 out of 99. Right? The closer this fraction is to 100, the closer this fraction is to a half, the better. I have 199, I have 99 marbles left. I have to have at least one red here. The more reds I put in here, the more blues I put in here, the smaller the denominator. The smaller the denominator, the further I am from a half. So this is the best I can do. And so this tells you that the solution is to have one red here, and then 49 red and 50 black. And so this is the non-calculus way to solve the problem. Okay, there was a typo on one of the homeworks For the normalization constant for the Gaussian, it should be 1 over square root of 2 pi. And for the first problem, all I care about is the total number of heads you see after the 2 sets of tosses. So imagine you are outside the room, you don't know which coins have been retossed, you just want to know how many coins ended up as a head.